Welcome. This is now the third lecture on Introduction to AI. And today we are diving deeper into the world of AI. And I'll go into the topic areas in a bit. And you can already see the topic on the screen. I have a very positive feeling of today, partially because I got away from the long meeting and now I'm here with you. I was also reading the feedback and I'm super happy that the continuing support. Last week I had 81 of you had written in feedback for the week before, and now was it 70 something feedbacks provided, and I went through all of them. Many of the comments were related to the content. People seemed very happy, but then there were also good improvement suggestions where two stood out. One was the desire to get some more technical examples, how things work deep down. Well, this is a very technical course, but I think we will get some details today. Then there was a comment that stood out because several of you had commented on the videos. And now I think you are maybe not the people who commented on that because you are here in person. But then those of you who watch the recordings afterwards, so there's something I hadn't realized with YouTube. So if you actually watch a very long video and there's a commercial break every 15 minutes or so, that can get a bit annoying in the long run. So it's kind of a trade-off. Previously we were using Panopto and there's no commercial breaks, but then based on previous feedback from other years, I decided to try YouTube this time. But I hadn't realized that there are these commercials that of course, interrupt things. But then someone pointed out when we were discussing this before that maybe it's also an opportunity to take a break, do some stretching, go and get a coffee or a drink, and so on. So you can also look at the positive sides. And of course, then if you come here in person, we don't have any commercial breaks here. We have one break typically, but there's no words from the sponsors, so to say. But I can have a look. Maybe I could also post the recordings in parallel on Panopto. This could be one option. Good. Any further comments or ideas before we get started with the topic? We're kind of halfway on the lectures after this one. So you have already kind of been traveling into AI for a bit with me. All good? Yeah, you remember the Nording policy. Exactly, yeah. Okay, so should we go forward? Good. Okay, so today we're talking about deep learning. And some outline. So we'll look into what deep learning is. I think that's sort of the first and foremost thing. And we have already discussed this in the previous lectures that deep learning pretty much is propelling the current wave and craziness around AI, even if it's just a subset of things, but it's a very visible subset of methods and models at the moment. I'll talk about neurons and networks and how that links to artificial neurons and networks. Then I try to highlight that deep learning is just it's not one tool or model. It's actually a whole collection of ideas centered around these principles that you can connect simple units to make something more complicated. And then there's quite a bit of examples. And it's actually been pretty fun preparing like lectures on deep learning for the past 5 years or so, because there's not much kind of in the examples that you can reuse the next year, because things move so fast. So if you think like 5 years ago, large language models, they weren't really a thing. They were something that didn't really work at all. We had just had the first successful generative image models. The results didn't look that good, but it was still like kind of impressive at that time. But now kind of things move so fast, and the things that you can do with the models is changing so rapidly over the years. So like I need to update all the examples basically on a yearly basis. Yeah, and I have a tiger here. The tiger is of course generated by a generative model. It's not a real tiger. It would trick me. I'm no expert on tigers, as you might have realized at this point, but it shows that maybe the tiger, like maybe deep learning is kind of the tiger of machine learning at the moment, at least sort of then if you think that how much publicity things get. Okay, so this is the day of the tiger, so to say. If we go back to lecture, the first lecture, I showed you this picture, and now you remember like AI is not just one method, one tool, one way of thinking. It's actually a collection of things that like bring a lot of different approaches under like the scope of AI. And then I showed you this. This is my view on how you could like project down different terms, subfields, approaches within AI. And last time we covered learning-based things, machine learning. And now, if we think that this journey now, what we are currently doing, so this third lecture is like going even deeper down. So now we consider kind of a subset of machine learning. Because deep learning pretty much makes up like specific families of models and approaches that are very flexible and can be trained for complicated data. So now like think AI, then machine learning, and then deep learning. Okay? If you want to kind of like build some hierarchies of things in your mind. What did we talk about last time? Who remembers? I see many of you actually attended in person last time as well. So I gave you this view on machine learning, and who remembers what the components were? Data, models and algorithms. Very good, very good. So you have been awake last time. And then we looked at what data was. And then we looked at different models. If you remember what the model did, what was the model? This was complicated. I think you asked a question about this last time.
Yes, I did ask a question. It was like how to embed your beliefs and what kind of mechanisms or processes were behind the generation of the data that you have to train.
So the answer that came from the audience was that the model is basically where you put your beliefs of what is generating the data. Kind of like your prior beliefs of what is behind the thing being like modeled. And we went through different examples of like models and model families. So now like it's a bit of a hassle because like if you think of a linear model that we used as a simple example, that's quite explicit. But then I talked about model families. What do I mean by that? You could say that, for example, deep learning kind of is just like, it's not like one specific model, it's a family of approaches how you can build models of similar kind. So that's kind of a model family. There was a question about this in the feedback. So today we are focusing kind of on the modeling part. We are still under the realm of machine learning. So we still have AIs that learn from data, AIs that then have something that is fitted to the data, and that's the modeling part. And then with different strategies and algorithms, how to combine the data and the model. algorithms. I think I mentioned like the secret sauce. That was the algorithms. Okay, so deep learning today is mostly concerned kind of with complicated data, models of specific structure that we will go into a bit, and then algorithms in how to train these beasts. Okay, now I need some coffee. Good. Okay, so if we think now about models and what do we want from these models? What we in deep learning actually want to do is to model complicated, chaotic data. And now if you think of what do I mean by complicated and chaotic, I actually mean kind of very everyday things. Things that we humans do not consider complicated or chaotic, but which actually appear super unstructured for a computer or a machine. And this is what I try to show as something as sort of like everyday. Data from the real world. That kind of data that we as humans need to process with our eyes, ears, and other senses. So I mean images, natural images, or natural audio, or text, like human written text, which is actually quite complicated when it comes to defining a structure. Think of how would you write down a mathematical algorithm or equation that could capture your beliefs of how Moby Dick is written, or the Kalevala, or something else, or describe a cat with an equation. It's super hard. So that's actually chaotic and complicated from the machine's point of view. So what we're actually interested in doing is having a model, and the model here now in mathematical sense means a function. The function is here denoted by f, where something goes in, that's the x, and that's what goes in is that complicated thing. Text, images, audio, things that can stream into your senses as well. And then we have some function that can take in that and squeeze out sensible information from that complicated input to get some output. The output being like a label, true, false, for example, whether there's a cat in a picture, or something else, a new snippet of text, or a new image. And I put this W here because it means that this function here would be parameterized with some parameters, some free number values that describe how it should behave. And we'll come into that later on. So models are basically functions, and deep learning provides a family of different methods for writing functions that are super flexible. Flexible in the way that they can fit to very complicated inputs. Does it make sense? Okay, so what you should get out of this is that we try to build complicated functions that are described by deep learning models, neural networks. You get there. So, deep learning could be considered a class of machine learning because it's learning based. We still have data. We will want to adapt those functions to observations. And they are kind of like models and methods. What deep learning per se is saying that the idea of deep learning is simply to use multiple layers of some sort of processing. You have multiple layers of kind of functions that extract features or transform the inputs. So, and this definition of deep learning doesn't actually involve anything about artificial neural networks. You can build a deep model by stacking basically any type of function after each other. But typically in machine learning, deep learning is almost used as a synonym for neural network models. So typically these nonlinear units and different layers are collections of artificial neurons. We'll go into that in a couple of slides. And everything that I talked about last time, about the data, about the ways of learning, like supervised or unsupervised learning. Do you remember what these were? Some of you are nodding. So what was supervised learning? When it's given labeled data. So you kind of tell what you want, kind of, when you train the model. You show that this is a cat, and this is a dog, and this is a cat. And then you want the model to generalize that when I just show something, the model should know what's in the image. How about unsupervised learning?
It was when you just give the data without any labels and then it sorts it by themselves.
Yeah. So then basically the answer was that when I give a method just data without labels, and it's supposed to kind of like build the knowledge of our extracting the knowledge on its own. For example, for then like creating similar new data samples. For example, you show a method a lot of images of cats or human faces, and then it should learn to generate similar images of cats or humans. And in deep learning, kind of the kind of sort of original motivation where you should have like different layers of things, kind of a hierarchy, would be that you would actually have the model learn like multiple levels of representations to form like a hierarchy of concepts. What do I mean by that? So kind of, we would hope that these complicated models would kind of learn to recognize that, oh, that's a car, and cars have doors, and doors have handles, and so on. Turns out that this is not how these methods work at all. It's a lot more complicated and more chaotic. And it's very rare that you can actually like see that the model would learn some like sensible hierarchy of things that would make sense for a human. It probably makes sense in some high-dimensional latent space for the model, but not so that we humans could actually understand what the model is doing. I've been talking about deep models and mentioning neural networks every now and then. And maybe it's pretty clear for you that I'm no medical person. I don't know that much about the human brain. But that I can say that artificial neural networks is not about replicating what happens in the human brain. It's more about something that takes inspiration of how the brain of like you and me or any animal works. So artificial neural networks are inspired by like actual networks of neurons. And if you think of like the human brain, we have a lot of these neurons, and they look something like this. So they are like inputs, and typically these inputs are connected to other neurons. Then there's something like electrochemical processing happening. The things coming in from the inputs are combined, and then there are some outputs that typically then connect to other neurons. And what happens in a single neuron is kind of complicated, but not overly complicated. It's kind of like understandable. And each of these neurons, they are connected to so many other neurons. So it's actually like a network made out of neurons. And these neurons are pretty simple. So there's nothing intelligent about single neurons. If you take a single neuron and put it in some liquid, so you can observe what it does, and there's no magic to it. It's a pretty sensible thing. But when there's enough of them, and enough means a lot, like in the billions and billions, and they're all connected and interact, they can power up something as complicated and weird as the human brain. And the key really is how they interact, how they connect, and then how they process the information and pass it on. And it's weird because each and every one of us carry around a brain. And still it's a big mystery to us how the brain actually works. So now if we think of them like, okay, let's take inspiration from that. Let's construct an artificial neuron. And this was kind of the idea already in the 1950s. Because if you remember the history of AI from the first lecture, that was sort of then when we started to have digital computers. And people had a hunch about how the brain works. So then like kind of a go-to method would have then be to, okay, let's just like replicate what happens to the brain in the computer and we will have flying cars and talking robots in no time. And as you remember, that's how people expected things to be. So the idea of taking inspiration from actual neural networks and neurons, replicating that in a mathematical model that then would be adapted or trained is old. But it's been a struggle for the field of machine learning and AI to actually get these things to work. Okay, you saw my sketch of a real neuron here. Inputs, something happens, outputs. Let's try to do the same in a very simple mathematical model. And I'm kind of both proud and not proud to say that this is maybe the most mathematical part of this course. So now, be with me here. So these x's here are inputs, just as in the artificial neuron. And the inputs here now are numbers. They are typically floating point, like decimal numbers in the memory of a computer. And there's a number of numbers here. What happens then is that they are multiplied by these w's, which are the model parameters. These are weights of the model. And now you might remember that I denoted in the function also the parameters with the w. So these are just numbers, but they are kind of the free parameters that need to be learned when we show data to this thing. Okay, so now what I've done this far. I have numbers and I multiply them with other numbers. Okay? Then I sum those results up. This is a sum. Then there's a very important part. Because this would be a linear model otherwise. There's something nonlinear happening. There's a nonlinear mapping that transforms this a single number here to another number in a nonlinear manner. I'll have examples of what that can mean. It's not actually there's actually theory for this as well. So it's actually shown that it doesn't really matter that much what kind of nonlinearity this is. It just needs to be nonlinear. And that's kind of interesting. And let's not go more into that. And then there's an output. And this output is also a single number. This is one single neuron. Who thinks this is AI? Is this smart in any way? You think it's smart? Yeah, I think it fulfills the definition of AI because it's something that you can fit the data, it adapts, and then it can act based on the inputs you give it. It cannot do that impressive things. Like a single neuron will not generate text for you. A single neuron will not generate cat images for you. Definitely not. And it's actually very sensible. You can actually see what happens. If you feed in some numbers, you can see that they are multiplied and summed up and so on. A word about this nonlinearity still. I said that it's typically something very simple. It can be something called like a logistic function, or a hyperbolic function, or a so-called rectified linear unit, which basically is a straight line like this, and then it shoots up. In the GPT-type models, it's very often something that looks like this, but it's slightly softer around here. it has empirically been shown that it works slightly better like that. But you could do a large language model with ReLU as well, I guess. So this, I mean, these are very simple nonlinear things. Just means that here, when the numbers are summed up, there's kind of something nonlinear happening to make the full system, then when you stack these, also nonlinear. There's a question.
Like, what do we achieve with that? Because if it's like just a kind of deterministic thing that we always perform the same operation, so it's how does it like add any sort of like information or like adjustability to the system? It's just like a deterministic step that we do. We turn like a number to a single number, and we always know what that mapping is.
The question from the audience is that this is like everything appears deterministic. How can this be kind of then actually useful?
I mean, okay, the inputs and the weights change, and like I see that okay, those can be like adjusted and like affect the input, but like the non-linear part like seems kind of like extra.
The nonlinear part seems extra, is the comment from the audience. That's a very good point. The thing is that if there would not be a nonlinear part, this is actually a linear model. This would be like a fully linear model. And that's a valid model. You can have a linear model as well. But turns out that if you model with a linear model, for example, images, it cannot actually learn anything complicated. So the nonlinearity here is important because that makes the larger model also nonlinear. Because if you stack linear models, the final model is still linear. So you need to have some nonlinearity there to actually make the model expressive. Now I see some nods from the audience. Does it make sense? Yeah. Because like a linear model is a great model. Many good things are modeled with linear models, but then actually to make things separate and be able to model things that fall on some complicated manifold, as for images, for example, then you need some nonlinearity in the model. Otherwise, you basically fit a high-dimensional plane into your data, you could say. Okay. And of course, basically any nonlinear function, or almost, can be used as an activation function. Not all work great, and they have different properties that they induce into the model, but these are maybe the most commonly used ones. So, that's then like the full artificial neuron. Okay, now we have like these single neurons, where there's something comes in and something comes out. And it's already a model, but to actually make it more expressive, let's stack such neurons next to each other. So collection of connected units of these artificial neurons, they can be composed into layers, so to say. So a collection of units that are kind of like at the same stage in the model are called a layer. And typically you might need quite many of these units to capture something that is interesting. How many? It depends on the data that you're modeling. Say if you're modeling images, you might need some hundreds per layer. And then like also depending on how complicated the phenomenon is that you're modeling. And then several layers then. It's still not deep. The deepness comes from having layers after each other. And now this links to how they interact, because each successive layer uses the outputs from the previous layer as the inputs. As you can see here, each of these nodes are like artificial neurons, and then the output is then connected as inputs to these next ones here. So these are called fully connected. All of them are connected to each other then, between layers. And now, like how many layers do you need? Well, it's a design choice. Remember, the model was where the person building the AI method kind of puts in their beliefs of what is sensible and needed. So now, like, how many units, how many layers, what kind of activation function, all these are decided by someone building the AI model. And having these things after each other makes the model super flexible, because then the different layers can actually transform the data into some other type of space that might be easier to handle then. Think of images. So passing the image through several layers can help actually map the image to a space where actually it's easier to describe like features of cats, for example. Still, stacking these things on top of each other makes things immensely complicated. And it's not human readable what is actually happening. And I'm quoting Arthur C. Clarke here, who wrote that any sufficiently advanced technology is indistinguishable from magic. And I would kind of relate that to, it's actually easy to understand how these neural networks work. The building blocks are very understandable. Someone with kind of like a primary school mathematics skills can understand how a single neuron works. But it's super hard to understand why connecting all these things suddenly produces something like GPT-4 or generative image models. So there's kind of this kind of like super simple, then just stack simple things together and suddenly something magical. And it's not kind of like an easy way to see that why it actually works. And it's not you or it's not just me. I think ask almost any expert in the field, and I think they can agree with this. I talked with some of the people who actually come up with these things in the first place, and this is from them. So believe me, people are a bit astonished that it actually works. And in machine learning, usually theory follows several years behind. So even if kind of like you can show that, yeah, making something complicated and flexible and fitting it to data should work, it's still a bit of like leap of faith that it actually works. I mentioned that these things are well suited for applications where the input is complicated. And complicated, I meant like images, audio, natural text, and so on. But all of these these are complicated only in the kind of sense that they are hard for the computers to process, like as is. But what kind of applies here is that typically through some nonlinear transformations, they can actually be mapped to some sort of sensible latent space where the information is concentrated. That sounded a bit complicated. I have an example. Like, for example, if you think of images, like photos, and last time I described that, well, images can be described by this grid of pixels with colored dots, basically. If I would take a random set of these colored pixels, it would look like this. This is a random image. What does it look like? A cat? Nah. It looks like a random set of pixels. Like, it doesn't look like anything. Okay, let's make another attempt. This is another random set of pixels. What does it look like? Like this is like back in the day when we had analog TVs. This was sort of then what you saw on TV if there was something wrong. And I could keep doing this to the end of time basically, and there would not be a cat or like in the infinite like limit, I could generate, of course, any image, but that would probably take a very, very long time and several attempts to get a cat image by randomly sampling pixel values. That just means that all the images that actually make sense to us humans are very rare in the kind of the uniformly random pixel space. And they are concentrated on some complicated manifold where the pixels have some sort of then like correlation structure with each other. And what these deep models do is that they find that manifold where actually all the sensible images live. Does it make sense? One person is nodding. Okay. If you think of then like that there's like this is a high dimensional problem. If the image is, let's say, 1,000 by 1,000 pixels, I could describe this with a 1 million dimensional vector. And so the problem is kind of like 1 million dimensional. But then actually all the cat images, or all the images of cars, or all the natural images, all the photographs, are actually more related than you would think. They all share certain features, certain type of structure. And these deep models find that structure in the images. Think of it like that. Can you accept that as a sensible explanation? Okay, some of you are nodding. Okay. Good. Typically then, if we have like a deep model, there are several layers of different processing happening. And there's a lot of like other operations also. There can be like subsampling and convolutions. I talk about that in a bit. But these real-world models typically have many layers, and remember that each layer has several neurons, and each neurons have several parameters. So the weights or parameters actually become quite many. And these are the things that you need to learn or train through optimizing the model. So it's like a big optimization problem, where you have your training data and you try to tune the model parameters so that they would kind of replicate the training data. And then you hope that if you can fit the training data with your parameter values, it will then generalize to new things beyond the training data. Typically, the number of parameters can be quite big. Like, for example, GPT-3 has 175 billion parameters. That's many parameters. And you remember that we talked about overfitting last week. So then, typically, if you have a lot of parameters, you also need a lot of data to avoid overfitting to the training data. Which means that these are pretty data-hungry models. And just like keeping all those parameter values in the memory of the computer is challenging, not even considering kind of then like handling the training data, that also takes up space. And all the compute when you need to then like train the model by passing things through the model and evaluating it. And this is where you need like graphical processing units, GPUs. And I don't know if you have followed the news, but for example, NVIDIA, which is the leading GPU manufacturer, they're basically making a lot of money at the moment. Because to train big image or text models, you need to have a lot of hardware. And NVIDIA is basically selling the shovels in the gold rush now. So in that sense, also the hardware is quite critical here, because big models do not run that easily on small hardware, and especially the training requires a lot of expensive hardware, but also then electricity and maintenance to run. And we already discussed this last time, but actually then like understanding and reading out what the model has learned, what the parameters mean and so on in these deep models is close to impossible. They don't really mean anything per se. For us humans. For the model, yes. For humans, no. I've thought about neural networks now as if it would be kind of like one model in a way that you then like train. But it's actually kind of a zoo of models. There's many different ways of building neural network models, deep learning models. So you could think of it as sort of like different families, or subfamilies or subcategories within like the broader framework. And this is actually like an actual like neural network zoo, and there are different types of models, typically like based on how the neurons connect and what kind of happens then. So depending a bit on that, are all the layers fully connected, or if there's some sort of bottleneck that you first have this many units and then you scale down that there are less units in the middle, and then again you scale up. There are a lot of like methodologies and theory of why certain things help for certain types of modeling and problems and so on. So there's really a lot of different approaches how to build and stack these neural networks into different structures. And they are not even all here written out. So this is just to give you an idea that it's actually sort of then like a whole toolbox of its own, depending on the problem that you're tackling and what you're doing, that what kind of makes sense and what is desirable. And I'll only go through some kind of typical ones that you might stumble upon, or that might be sort of like easily explained. I already mentioned that typically can also then like involve other processing. And for image models, I'll have some examples later on, but typically for image classification, if you're interested in finding whether there's a cat, for example, in an image, or recognizing a face in an image or so, then you kind of like know that, well, the best approach for this type of problem is to use a so-called CNN, as a convolutional neural network. So this is kind of then when you build the model, you sat on some course or read a book, and you know that for a problem like this, you should use this model family. And the CNNs are the go-to things when it comes to like image classification problems in many cases. So analyzing images, and why? Well, the convolution, which I have a slide on next, kind of makes it kind of like translation invariant. It doesn't care where in the photo the cat is. It kind of scans through the image. A bit like if I look around and someone asked me that, is there a lion in this hall? So then I don't need to separately check every seat. I just then like scan through, and somehow there's something probably convolutional happening by my brain that says that no lions in sight. Super bad example. Sorry for that. I need more coffee. Or less coffee, I'm not sure. So what does a convolution do? So basically, in a convolutional neural network, you kind of try to learn a convolutional kernel, so to say, which is something that is scanning for cat-likeness in this case. It wouldn't look like this. This is just an example. And then this kernel is kind of rolled over the image to make something that kind of scans for cat-likeness. And then this is fed to the next stage in the deep model to then like check whether there is a cat in the image or not. So that's basically what's behind CNNs. I have a couple of more model families to go through, but should we have a short break now?
Yes.
Any questions this far? Maybe you can think of questions during the break. Is 10 minutes good? Sounds good. Okay, let's continue 10 past following that clock. Let us continue. We are going through different types of models now, approaches how to build deep models. And autoencoders are a very prominent family of models that used to be kind of like state-of-the-art for image manipulation and generation before some of the other models that we are going through next were invented. So in autoencoders, the idea is actually quite smart. So the idea is that you have some input, be that, for example, an image, and what the neural network is supposed to do is to compress the information in this input to some low-dimensional coding, say to like a set of 100 numbers. And then there's another part that takes this 100 numbers and tries to reconstruct the image back from that. It doesn't seem very sensible at first, but what this forces the model to do is to actually learn something sensible about this. Because you cannot compress this image into 100 numbers. So this is kind of forcing the model to learn concepts like pose of head, size of nose, shape of eyes, smiling or not smiling. So the model is kind of like implicitly learning these things because it benefits it. It makes it better because then it can compress the information. So for example, this output here is not the same image, but it has similar features. The person kind of like, if I would describe this person to you without you seeing this, and you would need to draw an image. So if you're really good at drawing, you could probably, based on my description, draw this, and then we could compare whether the input and what you draw actually resembles each other. So, as a byproduct of this, the latent space here can actually be used then for manipulation. So for example, if you then can recognize which direction means smiling, you can basically have kind of like tune that dimension to make some image like smile that is not smiling, for example, or change hair color or shape of nose or so on. You can manipulate the image, the output, by manipulating the kind of the encoding, so to say. And this is an example of unsupervised learning, because we just give it data and it tries to build a model that can replicate that data. And as I said, it learns a representation. So it can be seen as kind of like representation learning. And both the encoder and decoder can also be then used separately. So then, once you have trained a model, you can just throw away the encoder and just feed in random numbers here and decode them to create images. So then you have a generative model that can generate new images. Pretty cool. Okay, next family of models. Recurrent neural networks. These are used for very different things. So these are basically used for temporal sequences, things that happen over time. So like think of things progressing, like jumping from one state to another. Basically time series, in other words. And these are typically used in like handwriting recognition or speech recognition, where the data comes in as a stream. It's kind of something that kind of doesn't really end, but where there's like a structure over time. So then the model family of choice is recurrent neural networks. Okay. So different applications require different types of model structures. This is maybe what I tried to tell you. Okay, I mentioned that autoencoders were the state of the art, the best of the best for image generation, until kind of the field of generative AI was formed. And this is yet another hype term, kind of, something that is now in all places. And there's nothing special about generative AI. And the idea is pretty simple. So basically, the idea is that we have some simple way of generating random numbers. And then we have a model that can take in those random numbers to form kind of complicated things. So we have, say, like this, like complicated data distribution would be photos of cats, or human readable text, or almost whatever that you have a lot of data of. And then what the generative AI is doing is taking in some simple random numbers and transforming those to something very complicated. And that's kind of called the generative process. So it's kind of a mapping, basically a function that takes in random numbers and has been adapted to data to create random samples from data sets that has been trained on, that resemble the training data. And a prominent family of approaches or family of models in this space is called generative adversarial networks, GANs. And I'm taking GANs as an example because it used to be the state of the art for generating images. And it's still like very good at certain problem areas. But most of all, GANs are a very interesting construction. A GAN is basically a two-player game, where there's one player. The players here are basically neural networks. So player one is a neural network or deep learning model, and it's called a generator. And the generator takes in random numbers and tries to generate images, for example, in this case. Okay. Player one cannot see any data. That's what player two can. So player two is also a neural network model. And player two has access to the training data. And what player two tries to do is to determine whether the image generated by player one is an actual image from the training data or not an actual image from the training data. And at first, when they are just beginning to learn, player one sucks at generating images, and player two sucks at recognizing real versus fake images. But they grow together, they learn in tandem, so that player one gradually learns to trick player two by getting better at generating images. So probably after some million steps, it's this good. And at the same time, player two learns to be better at telling apart whether this looks like this. And because they kind of, like player one and two, they compete in a way, which kind of drives them both to be better. So that's why kind of like over time, player one learns to generate very good images. And player two learns to be pretty good at telling them apart from the real images. So they kind of like strengthen each other. Question from the audience.
In this slide, what exactly are the random numbers? I'm guessing, is it something that comes from translation of text, which I give to the generative AI? When I say generate the image of a square, a cube, something for example.
The question from the audience is that what are the random numbers? Do they have something to do with text? No. This is a generative image model. The random numbers are really just random numbers, like you would roll dice, or in reality they are pseudo-random numbers, typically from a Gaussian, high-dimensional Gaussian. But they really are just random numbers that don't mean anything. They are just random set of numbers.
And is that random number seed?
Sorry?
Is that the seed?
The question is, what is the seed? Yet, typically for practical purposes, you fix the seed in the beginning, but then the idea is just to have actual random numbers that you would actually get samples to learn to map from some random set of numbers to a random set of images, basically.
But then where does the player one get its commands from? What does it generate out of random number? It could generate anything.
The question is that where do the player one gets its commands? How does it know what it should generate? You cannot command it. It's a purely generative model. It generates a random sample from the data distribution. So if it's been trained on human face images, when you throw it a random number, it generates some face. You cannot control it. This is a purely generative model.
Does it have a practical use, this model?
The question is that, does it have a practical use? That's an excellent question. And when these GANs came out, there was a lot of criticism that, oh, you can generate fake human faces. Good job. What will we ever need that for? Except for creating fake profiles on the internet. And that's a valid point. So in the beginning, this was mostly out of academic interest. But then, especially then, like later on, when we learned how to control the generative process, and that basically now gives us these like multimodal models where you can actually influence the generative process so that you can specify that you want to have a cat dancing on Mars. So then it's actually influencing kind of the generative process that you get. But then that's kind of a slightly different story. Typically you still like have these purely generative models are trained to do this. And for example, the large language models, like the one you tried in the exercise, like the default configuration is that you provide random numbers to it and it provides text, some text, completely random. One time it might talk about the sunset, other time about spaceships. Like it's just creating random text. It's a generative model.
Why is it that these GANs generate fake images that are good or indistinguishable from real ones, instead of just converging to generate real images that are exactly the training data?
The question is that why do they actually generate similar images as the training data and not exactly the training data? So we talked about overfitting last time. So then basically if it would then like learn to create only the training data, that would be then like overfitting to the training data. And quite frankly, training a GAN is not easy. And that's maybe one of the reasons why we have other types of models on the next slide. Because you're basically trying to train two models. And what often happens is that one of the model learns quicker, kind of. And then overwhelms the other one. And then the whole thing breaks down. And then you kind of collapse into some local mode that it can only generate one type of image or so on. So it's actually tricky to train these GANs. Examples of GANs, there are a lot of like methods and things built around GANs. But for example, this particular GAN here has been trained to convert input images into art of like different styles. So these are the inputs and this is the output of the model. So it can generate then artwork in the style of these masters. So that's like one use case of GANs. GANs are not the state of the art anymore. And most generative image models that you probably use are nowadays based on so-called diffusion models. And diffusion models are actually a different type of smart construction. So there's no two players that learn in tandem or anything like that. Instead, there is first a process that destroys data. So basically, say that you have real photos. So then you actually have defined a process that destroys the information, for example, by adding noise, step by step, like this, so that you end up with just pure random noise. And what the diffusion model does, very much simplified, is that it learns to revert this process. So it basically learns that you can start with noise and go the other way around, like de-noise, remove noise. And voila, you have a generative model. Sounds simple, it's trickier than that, but basically, like diffusion models are all based on some way of destroying the information and then like doing the reverse, then like restoring the information then based on that. Here's an example. So basically, this particular diffusion model is de-blurring. It can create sharpness out of a flat color surface. So for example, here it starts with a flat surface and then kind of it's like build structure out of the fog, kind of, to create cats in this case. It's been trained on animal images. Okay, one more concept to bring us into kind of the state of the art, so to say. Transformers. And this is a concept that is very important for example, the large language models that we use nowadays. So a transformer is a deep learning model that utilizes the mechanism of attention. And attention means that it kind of pays more attention to certain parts. And the idea is to mimic like cognitive attention, like enhance the important parts while they're kind of dropping the parts that aren't that important. And we humans are really good at this. Somehow, for example, when we read, we can actually ignore a lot of stuff. We just pay attention to those parts of the words that are important, and somehow this is built into us. And this is also what is very important in this like big NLP, natural language processing models, for like machine translation, text generation, and so on. And like a prominent example of this is like the GPT. The T there stands for transformer. That basically then like is very good at looking at structure of text and then generate new text. You have all used ChatGPT. And the same applies now to those generative image models where we can provide something that biases the generative process. And typically now they are diffusion models in many cases, and what is kind of biased is the generative process. You remember like going from the random numbers to the data distribution. So how that trajectory then kind of like goes, what is like pushing it, that's the text. That is typically processed through a other neural network model. And basically then, if I want to generate images of a professor in a bow tie presenting to a diverse audience, I can get an image of that. Or a painting by Albert Ehrenfeld of an old man checking his phone in the kind of like a oil on canvas painting. And now again, what has happened is that the model has learned to extract relevant information. It has learned to extract the concepts of old man, smartphone, Albert Ehrenfeld, oil on canvas, and so on. And it can kind of combine these in some like complicated latent space that we humans cannot understand, but it can interpolate there. We can also generate images based on images. And this is actually interesting because if you look at this picture, drawn by a 3-year-old, so I can tell that there is a person holding a balloon, and then there's a bunch of stars and the sun. And I think it's great, but it's quite abstract in a way. So this is kind of like a grand challenge also for like a big image model to like understand what is where and how. So now I can feed this in to a generative image model and then bias that encoding to modify this. And now I'm modifying it. I would like this to be slightly more than like realistic, kind of as if drawn by someone older. And I get this out. And interestingly, the concepts are there. The human holding a balloon, the stars are there, and the sun. So clearly, the model learns to extract kind of the important bits, a bit like we humans also extract things when we look at it, even if it's abstract. And we can continue. This is kind of same content, but again, kind of like straying further away from the original input. So the human is there, the balloon, the stars, the sun. And of course, then with these neural models, we can then also then like actually model the real world. So this example here shows about examples collected, for example, with like handheld cameras or smartphones. So that's the input now. But then the neural model can actually then like create views from other angles, for other poses that have not been observed, to kind of like interpolate. So you can see that those parts that were not observed at all are kind of black here. They are like the thing disappears into a fog because the model doesn't know what should be there. So these aren't videos, real videos. These are actually being sort of rendered by a neural network from different points of view than were actually observed in the beginning. So this is collected by an iPhone. I don't know what happened. Let's hope it comes back. Okay. Deep learning is great. You can do all these great things. But there's also a bunch of problems worth mentioning. I'm quoting my colleague, who's a professor in the UK, who said these wise words. Who said deep learning is like traditional Chinese medicine. What does it mean? Well, apparently traditional Chinese medicine is something that's developed over thousands of years. And pretty much through trial and error. So like you try different herbs, sometimes you die, sometimes you get a headache, sometimes it actually cures you. So with a lot of people trying different approaches, you can actually like find things empirically. And unfortunately kind of, lots of the deep learning development is pretty much based on people just trying different things. Because theory follows behind, and it's just quicker to try things. So in that sense, it's kind of like traditional Chinese medicine. I mentioned this many times. It's very hard to try to understand what these deep models are actually doing. This is a car detector. So this is kind of like, this is from a blog post by OpenAI. Them trying to read what is happening inside the model. And you could maybe tell that there's something window-like, car window-like here, or there's something car body-like here, or like something like some like wheels from different points of view. I don't know. Hard to say, but looks a bit like crazy. This would be like a pose invariant, like a dog detector that can detect dogs from different points of view. So there's something dog-like maybe here, hard to say. And then also then like even if these models have been shown a lot of data, like millions, hundreds of millions of images. And for example here I'm generating like an image with a Tesla on the left and a horse on the right. Dark background, professional photo. Cool. Look at the horse. How many legs? 5 legs. How many 5-legged horses do you think was there in the training dataset? Yeah, I don't think, probably not that many. Or the model had clearly not understood that, well, animals typically have like an even number of legs. So it's pretty interesting, because that's something that we humans learn pretty quickly. You don't need to see many horses to realize that horses typically have 4 legs. Yeah. So it's just like an example of that. It's actually hard to understand what the model learns. And we shouldn't kind of like, we might think that we actually understand it. We probably don't. These are also huge models. They are like bloated and data hungry. They need so much data. And that leads to like questionable data and energy efficiency. They are like kind of too big and too hungry for what they do, in a sense. And this is in Finnish, just to highlight that in certain languages there is less data. So I'm asking, this is an older version of ChatGPT, what it can tell about poo sausage, kakkamakkara, in Finnish. And it tells that this type of sausage is a Finnish traditional food. It's a delicacy that is often like eaten with potatoes, and it's often used in parties and sold in marketplaces. So the extrapolation kind of, or even like the interpolation capabilities are a bit questionable. Because if I ask my kids what poo sausage is, they aren't saying that it's something that you should eat. Yeah. So Gary Marcus, who is a very known skeptic about like these large AI models, he once said that the knowledge gathered by contemporary neural networks is spotty and pointillistic, arguably useful, certainly impressive, but never reliable. And I think this is very well said. So I would not like to be on a airplane, where the pilot has been replaced with a GPT model. Because there's no guarantees that the plane would fly safely to where it's supposed to fly. Probably most of the time it would be fine. But I guess no one can guarantee that the model would do something completely crazy at some point. Okay, we have a bit of time. Any questions about the different models we covered?
Yes, we have images and text. How about audio?
Great question. The question is that we have images and text. How about audio? I was thinking of this, and I almost added an example of audio, but then I was maybe lazy, or then also like concerned how that would then fit with the rest of the slides, so I didn't do that. But everything applies to audio as well. So the leading audio models, both for like turning audio into text and text into audio, are all neural network based. So that's like a very typical use case, but I don't actually have any example of audio here per se.
Okay, so it doesn't use any of the deep learning models?
Yeah, it certainly does. It's based on deep learning, but none of my examples on this lecture are audio based. I'm sorry. And actually I considered this yesterday, and I can tell you here exactly where I almost included an audio example. Very good, well spotted. You caught me there. In the back.
Sorry, just going back to the GANs. If I were to try and program the GAN from scratch, considering the first layer, how do you actually start with that? Does it still have back propagation to minimize the error, and when you terminate the problem and say it's trained now?
The questions about the GANs, and then how to actually then like build the model and train it. And yes, so you basically train these two models jointly. So you have two neural networks, and then the actual, then like the models are trained jointly. You have parameters for both models. You do backpropagation and train them just as you would train one model. There's a lot of special things with GANs and how to actually get them to train and so on. And then going to these high like resolution images, that's a whole story of its own. But GANs are slightly tricky, but a very interesting construction with kind of the nice interpretation of having like two players competing with each other. Good. There.
Can you give some more example on the application on the GANs?
More examples on application of GANs. GANs are really used for like generative like modeling, typically for images. I think like the image models, like that was sort of then like the big victory of GANs and why GANs became so kind of famous. The NVIDIA people here in Helsinki being the first to actually use GANs for generating high resolution human face images. That was kind of like big news back in the day. So it was like a great victory for like generative modeling in a sense. And of course, GANs can be used for generating almost any type of images. For example, the lion on the second slide, that's generated by a GAN. So it's a good example of
talking about the human faces, so there is the second phase of it. It needs to access to the real data, right? So how is it? I don't know how to describe it, but let's say to protect the data of the person, and it needs to access the real data. How does it work with the legislation?
There's a question about, because the GAN, or basically any generative model, needs access to the data.
Yeah.
So then like how does that fit with legislation and data use? We'll talk about ethical aspects on the last lecture, but then this is a very interesting question. And for example, OpenAI is not disclosing what data they are using to train their models. And this is a good example of that. It's considered both a trade secret in a way that you don't want to reveal your tips and tricks how to train to other people, but then also then like, especially in the early days, like scraping data from the internet was the typical way. And I think that's still the dominating way of training these generative models. So it's images scraped from the web all over the place. That's been...
It's just take the images that's easily to be accessed.
Yeah, like, and these are so data hungry. These the big models, you basically need all the data that you can just find. And that's what has really happened in the past, I would say. In the back.
Yeah, you were saying about these big models being like energy inefficient. So are we going to run into problems with either not having like enough energy to kind of continue developing these, or like running out of money to pay for the energy, or is this like not an issue?
There's a question about energy efficiency. I mentioned that these are very energy hungry. So will it be a problem that we either run out of energy or run out of money? So I think already now actually training like something on like GPT-4 level of level of compute, that costs millions and millions, tens of millions of euros to train like a huge model like that. And of course that means that it's not so that I can give to you as homework that, well, now you go and for next Tuesday you train your own GPT-4. That wouldn't be feasible nor sensible. And of course then, because of the energy use, it's actually recommended in many like publication venues to report how much energy like did you need to train these models and so on, which makes sense because that's actually something that should motivate us as researchers to build more like data and energy efficient models, because it doesn't really make sense that you burn like oil and coal to train the next cat image generator, I find. Good. Let's go through some examples. So the first set of examples here is that basically I label this as models that have sense and sensibility. and maybe some senility as well. So let's start by a generative image model where I provide a prompt, an everyday looking photo of a family on a hike with their dog. Their van should be in the background. And I use Dolly Tree. I could use something else. You will be using a open source generative model that is pretty good, I find, next Tuesday. But I use Dolly Tree here, and I get something like this. And, well, and let's consider this as an input for the next stage. So this is just, I could have used any photo, but I chose to generate one. I took this photo, and yesterday I updated my scripts, and there's a line of models called YOLO, you only look once. You only look once. And this is already the 8th generation of these models, and they are typically really good like CNN-based models for classifying like everyday objects in or things in images. And this is what I get out. So it classifies that there's a person with the 95% like certainty here. There's a second person, a third person, a car, a dog, backpacks, and so on. Okay, a bit hard to read like this. So, but this is image classification. Remember that from last time. Whether there are things in the image, and then I have like provided the bounding boxes. So basically I get the image classes person, car, dog, and backpack. I get that those are in the image. I can use YOLO for doing image segmentation as well. So I continued, and I did, this is like semantic segmentation. It colors the humans, the backpacks, the car, the dog. Looks sensible. I can also use YOLO to do so-called instance segmentation that actually can separate out that this is one person, this is one backpack, this is another person, another backpack, third person, a fourth person, and so on. And this is a dog. So you can actually say for every pixel to which category and to which entity it belongs. And then there's the car in the background. Okay. And this required maybe, I would say, 10 minutes of coding for me to do this yesterday. So this is not really rocket science to use these models. Training them, maybe a bit different story. But then like these pre-trained models, super easy to use, work pretty well. Okay, then we can move to something a bit more maybe interesting. Because none of you are impressed anymore that we can recognize dogs in images. I think I'm old enough to think that's pretty amazing, because when I started, we could not do that. So I think it's still amazing. But yeah.
Can I ask a question?
Yeah.
So we've been talking about the image recognition. What about this annoying, can you click on all pictures with a bike or a person or what's typically called caption in the internet? So where are they with this stuff? Because I still have to click on pedestrian images and so on.
The question in the audience is that why do we still need to click on pedestrians and traffic lights online when logging into places? Excellent question. I have no clue. Maybe it's because of then if you try to break those at scale, it still requires a lot of compute to run models and so on, and which costs money. So maybe that's the motivation. Hard to say. Yeah. But there's less of those nowadays, because back in the day, whatever you did, you need to tell that which numbers are in an image and so on. I haven't been seeing those in a while now, for good reasons maybe. Okay, question.
Could I just add to that I'm pretty sure like when there's like a captcha, all you need to do is click on the thing and it lets you kind of through. I think the way that works, that a computer will like, the cursor will draw like a perfectly straight line to the thing you try to click, but it detects if you're a person, if your line is kind of wobbly and chaotic, the path you go to the thing that you click.
There's a comment from the audience that like the usual tell what's in the image has been replaced pretty much by analysis of often like the user like interactions to basically are you like a robot that draws a straight line with your cursor, or is it more than like human like behavior of what happens? And that's probably very true. Okay, so now describe this describe what happens in this image. This is a so-called like multimodality. So there's an image input and a text prompt provided to the model. And now again, there's there's just different kind of parts of the same big model that is like combining inputs from the text part and the image part. And GPT-4 gives something like this. In this image, there's a family of 4 enjoying time outdoors. There's a man and a woman, likely the parents, with 2 children, a boy and a girl. They're all smiling and appear to be on a hiking trip, and so on. Which kind of all makes sense. And this is probably something that is kind of maybe regressing a bit to kind of a default setting. But I think that if you would ask 100 people to describe this image, this would probably be kind of the average kind of like description. And that's still pretty impressive, I think, because the model has seen so much. So it's kind of like, it's not only describing what it sees, but also what it assumes from the image. It assumes it's a family. It sees, it can probably recognize it like the humans, a dog, forest, and so on. But then it can kind of like go steps further from that. And that's kind of the impressive part, because it has learned context, a bit like we humans have, from other data it's seen. Okay, we still have a bit of time. I'm talking about context and something called foundation models. And foundation models is just a fancy term for very big models that have been trained with a lot of data to kind of like be foundational in the sense that they have learned a bit of everything, a bit like kind of like we humans have. And this case study is now based on me, partially because I wouldn't dare to put anyone else's image here. And the task now for the model is this. This person in the photo shows up for a job interview in a tech company. Purely based on the photo, what is the first impression? And now I'm asking you. The task is to list 3 positive and 3 negative things. Anyone with some positive things first? This guy shows up for an interview. This is from my homepage. Now you can try to flatter me.
He's quite sharply dressed.
Sharply dressed, thank you. Anyone else?
Well-groomed.
Well-groomed, thank you. Any third compliment, positive thing?
Good posture.
Good posture. Do you have something else?
I'd say that seems serious about it.
Seems serious about the thing. That's good. Okay. Then the harder part, the negative factors.
There's a spot on your collar.
That's true. I never noticed that. There's a spot in the collar. Yeah, that's a very, very good point.
You didn't have a jacket on.
I didn't have a jacket on.
Simply went with the vest. Which shows that while you are serious, you aren't too serious.
That's a negative thing.
You would have been more positive with a jacket.
Okay, it would have been more better with the jacket on. Okay, that's a good point. Anyone else?
Too formal.
Too formal. Very good point. Anyone else? Should we ask the AI? Positive things. Professional appearance. Confidence. Direct eye contact. being prepared. It's good to be prepared when you go for a job interview. Okay, how about the negative things? Overly formal. It's still like, it's a tech company. So will I fit in? Is maybe the question. Lack of personality. That's a tough one. Expression. Like, am I actually enthusiastic and interested? It's a good question. So actually, I think it did a fairly good job. Because it had maybe like similar context as you have. I don't know if I should be worried or happy about this progress. Yeah. Okay, we are almost running out of time. So time for a summary. Today we tackled the lion or tiger.
Is it a lion or tiger?
It's an image generated by a certain model. It should be a lion in this case. But then I had a tiger on the other slide. So deep learning is a class of machine learning models and methods. And the deepness there, it doesn't mean that it's somehow profound or some deep meaning to it. No. It just means that there are multiple layers of nonlinear processing happening, where each successive layer feeds into the next. And these models are capable of great flexibility in feature extraction and transformation. And deep learning produces the state-of-the-art results for image, audio, and text modeling. Remember these things, and then that's good. That's good for deep learning. Questions about deep learning? There's one?
I guess then it doesn't cover video for the time being, only image, audio, and text.
There's a comment that video is not covered. That's a good point. I had the example of Sora last time, and it's actually like it's a deep learning model, combining like building blocks that we went through today. But then like it's a sequence of images. It's still like in the realm. This is also like the state of the art for a lot of other things, like molecule modeling for drug discovery. Other types of modeling where the problem is complicated. So deep learning is used for a lot of different things. But typically, things that are complicated, like molecules, chemicals, images, video, audio, complicated things, so to say. Okay, what next? The second computer exercise is next Tuesday. You get to play around with a generative image model. Super cool. The next lecture is on Friday next week. And the first hour of the lecture, we will have a visitor. We will have Meri Haataja, who is talking about getting practical with responsible AI. And that is pretty cool. And because it's an in-person visitor that we have, and it would be optimal if also you could then like interact and ask questions, and there would be some discussion. I'm actually this year providing 2 bonus points for attendance. So it doesn't count against kind of like, you can still get like a 5 full points, but these are actually like additional bonus points that you can get by showing up and interacting then. Good. Any questions still? No? Have a good weekend and see you next week.